Today's discussion will be on non-deterministic finite automaton. In short, we can say NFA. It will also cover the syllabus under Module 1 called regular languages according to your syllabus. So let us see what non-determinism is. A non-deterministic finite automaton has the power to be in several states at once. As we have already discussed in our previous lecture, that unlike DFA, in case of NFA, it can move to more than one states or getting a particular input. Right? So this is the power of non-determinism. This ability is often expressed as an arbitrary to guess something about its input. So where there is a guess type of thing present, or where there is a guessing is required, we need this NFA. We will see how to design an NFA. So when the automaton is used to search for certain sequences of characters, example keywords in a long text string, it is helpful to guess that we are at the beginning of one of those strings and use a sequence of states to do nothing, but check that the string appears character by character. So in this kind of situation, where there is a keyword searching in a long string, so we have to guess something. So for a particular input, we just guess to move to another input and so on, and ultimately we will check whether we are moving in the right path or not. We'll see. Now if we have to define non-deterministic finite automaton informally, so what it will be like this: like DF and NFA will also have a finite set of states, a finite set of input symbols, one start state and a set of accepting states or final states, a transition function which we shall commonly call small delta. So the major difference between NFA and DFA lies in this transition function only. What it does in case of DFA, as we have already discussed, for a particular input, the job of transition function is to mark that for this input the transition will be between this state to another state. But in case of NFA, it can be more than one, means on getting 0 at a particular state, it can move to more than one state. So here the difference lies between DFA and NFA. So in NFA, this delta or transition function is a function that takes our state and input symbol as arguments like DFA, but returns a set of 0, 1 or more states. Rather in DFA, returning exactly one state was must, right? So in DFA, it was must to return back only one state, but here it can be 0 number of states, it can be 1 number of states, it can be more number of states. Next, we will see a very simple example of NFA. What it is doing? It accepts all and only the strings of 0 and 1 that end in 0, 1. So as the trick that any string ending with 0, 1, what can be the smallest string? 0, 1 only. So here start state is q0, end state is, or final state is q2. So the minimal string will be 0, 1. So on getting 0, 1, we will just proceed to the final state. Now you can see here we have shown two different transitions for 0 at q0. On getting 0, it can be at q0, on getting 0, it can move to q1. So this is the basic difference between a NFA design and a DFA design. So what it is doing, as in our first slide we have seen, it is just guessing. So for 0, it can be at q0 or else it can move to q1. Later on it will check which one is a better option. Means the thing is like this, that if we try to design a machine or finite automaton, firstly we will design an NFA, means we will guess that for getting that on getting 0 at q0 we will be at q0 or we can move to q1. So out of these two we will ultimately choose one, and gradually we will be converting our NFA to DFA. We'll see later on how to convert NFA to DFA and so on. Next we will see the formal definition of NFA. It is very similar to DFA. As you can see, it is also a 5 tuple notation. Here again we are depicting the machine as A. It is consisting of 5 tuple, namely q, sigma, delta, q naught, f. It is very similar to DFA, Q is the set of states or finite number of states. Sigma is the input symbols, delta is the transition function, Q naught is the initial state, and F is the set of accepting states or final states. Here only the difference is with the transition function, as we have already told earlier. In case of DFA, it will generate exactly one state on getting one input, but in case of NFA, it can generate no state, one state or more than one states. Next, we will see an example. We have seen one figure 2 slides earlier. So there were 3 states and input symbols were 0 and 1. Transition function was delta, and then Q0 was initial state, Q2 was the final state. And if we just generate a transition table corresponding to that transition diagram, you can consult that diagram. You will be able to see on getting 0 at Q0, it can either move to Q0 or Q1. So the formality is to write like this. Within second bracket, we have to separate the states with comma. Fine. So on getting 1, it will move to Q0. On getting 0 at Q1, it will do nothing. So it is generating 5. And you can see for the others the same way. In case of NFA, it is mandatory to keep the states within braces when you are depicting it in the transition diagram table, right? So next we will see what perfect guessing is, right? There are 2 ways of intuiting non-determinism. One of them is perfect guessing. So we can view non-deterministic machine as having magic superpowers that enable them to guess choices that lead to an accepting state. If there is at least one choice that leads to an accepting state, the machine will guess it. If there are no choices, the machine will guess as any one of the wrong choices, right? So what here, since guess paradigm acts, so what the machine will do, it will, for a particular input, it will guess one, and if it is correct, it will keep on moving, and if there is no choices, the machine will guess any one of the wrong guesses, because there are no correct guess available. And later on we will see how to reject this one. And the second one is called massive parallelism. What is it? An NFA can be thought of as a DFA that can be in many states at once. At each point of time, when the NFA needs to follow a transition, it tries all the possible options at the same time. Start off in the state of all the states formed by taking the start state and including each state, and that can be reached by 0 or more Epsilon transition. We will see an example of Epsilon transition. So it is just guessing. Ultimately the thing is, it is just guessing. When you read a symbol A in a set of states S, form the set S dash of states that can be reached by following a single transition from one state in S, and your new set of states is a set of states in S dash plus the states reachable from S dash by following the 0 or more Epsilon transition. So what it is doing, what is the beauty of massive parallelism is, firstly we are having a form a new set. On reaching to the new with the help of the transition function, on reaching to the new state, we are keeping on adding the new discovered state to the existing one. So in this fashion, we can, by just guessing, we can ultimately move to our goal. Next we will see how to design NFAs. The main thing behind the design of NFA is guess and check. What guess will do, out of various options available, it has to guess one and check whether that guess was a bad guess, or it was a wrong option, or it is a correct option. We will see an example. What it is doing, they are asking to design a machine, a finite machine, where the string ends with 010 or 101. So from the start state, it can either accept 010 or it can accept 101. So there should be at least 2 different final states, right? So what we will do, for the simplicity, we will find just first make 010 acceptable, and for another 101 acceptable. Now, so what we are doing, we are guessing, if we get 2 consecutive zeros, we are keeping it there. On getting 0 at the final state, we are coming back. In this fashion, you can see different transitions are given. So these are all the guesses, right? Now how to check which are okay and which are not. So if you've seen from this diagram, if you move in this path 0 1 0 and another one is 1 0 1, my string will get accepted. So there can be any number of choices anywhere else, but this should be the minimal combination. So here we can see that at the start state there can be 0 and 1, anything, right? So either it can be in the start state on getting 0 or 1, or it can make two different transition. One is moving upward with 0, another is coming downward with 1, as depicted in the diagram. So here deterministically we are checking whether that was right to do so or not. So on checking it, we can see that if we keep this number of choices, it will be okay for our machine to work. Next we will see and so this is a demonstration of guess and check. So next we will see the NFAs with epsilon transition. So what is the meaning of epsilon transition? What it is doing, consider the NFA, it is named as N3, has an input alphabet 0 consisting of a single symbol. An alphabet containing only one symbol is called a unary alphabet. So what we are doing, if it consists of single zeros, it will be accepted, and for rest it cannot. So here we can see that we can just mark, you can ask that why you have given this epsilon transition. For the simplicity, you can even discard this epsilon transition. If we make those final state as single or as the initial state only, so for 0 number of zeros, it will be accepted. So here we can also make one initial state and can move some epsilon transition, that with no value of no input, it will ultimately move to the final state. Fine. So this is an example of epsilon transition. You can consult any book and can find more examples there. Next we will see some example. Here it is asking to draw an NFA for the given table or given transition table. What you have to do here, the second brackets are missing actually, you have to keep all the states within second bracket. So on getting 0 at q0, it can move either to q0 or q1. So first our job is to another thing, q3 will be of double circle, right? q3 is not the initial state, it should be a double circle, it is final state. So what we will do, we will mark 4 states. q0 will be the initial state and q3 will be final state. So on getting 0, we can move to q1 or can stay at q0. So you can just convert this. Only the change you have to do is just double circle q3. It is already double circle in the diagram. In the table you can single circle q3 and remove that arrow, it will be perfect, and put those states within second bracket. Next we will see more examples. Here we have already seen this example beforehand. It accepts all the string end with 0 1. We have seen it, we are revisiting it again. So it is ending with 0 1, and for any number of strings before, we can make it move on q0 only. So if we had to design DFA instead of NFA, we can mark only for 1, it can be at q0. We cannot make the transition for 0 to both q0 and q1, right? So this is the difference between NFA and DFA. So for NFA, we can show the transition for 0 at q0 it can move to Q0 and it can also move to Q1. Next, one more example. Here it is asking for to design an NFA in which double 1 is followed by double 0. So we will first design two separate means we will come one by one. So what it is doing, first it is double 1. Double 1 means it can move from one state to another with double 1. Here Q2 is the final state in the first diagram. And again, if it follows it double 0, so we will add more states and can make Q4 the final state. So the minimal string will be 1 1 0 0. Now we have to show the other transitions. What it will, if it gets 0 or 1 at Q0, it can be there. So again, if it is DFA, we can mark the transition for 0 only at Q0, but since it is NFA, we can make the marking for both the transition, that is on getting 1 at Q0 it can move to Q1, or else it can stay at Q0 only. Fine. See one more example. What it is doing, they are asking to design a machine where third symbol from the right end is always 0. So for the third symbol to be from the right end to be 0, in other way around we can think of the second symbol from the first end, or the first symbol from the first end can be 0 only, right? So either the first symbol can be 0 or the second symbol can be 0. So the easiest way, you can see, for Q0 it can either accept 0 or 1, but the second transition should be 0 only, and then it can be 0 1, or again then it can be 0 1. So this is the ultimate design. And this is the end of this lecture. In the next lecture we will see how to convert a given NFA to DFA. Thank you.